Okay, for example 1, the first thing we need to do is we need to replace the negative cosecant of x with its reciprocal identity. So we have the limit as x goes to negative pi over 2 of negative 1 over sine of x. And then we're going to do direct substitution. And I know sine of negative pi over 2 is negative 1, so I got negative 1 over negative 1, which is the answer of 1. In example number 2, I tried direct substitution, and I get a number. So let's see, that gives me a negative 0 minus 0 plus 12 over 0 minus 3. So that would be a negative 12 over a negative 3, which is a positive 4. Okay, and number 3, when I try direct substitution, I get 0 over 0, which is the indeterminate form, so that means I need to do some sort of algebra. I notice I have a radical and a binomial in the denominator, so I'm going to choose to rationalize the denominator by multiplying the top and bottom by the conjugate, which is square root of x plus 3. Multiplying the bottoms together, I end up with x, then the two middle terms cancel out, and then minus 9. So I know I can cancel out the x minus 9 from the top and the x minus 9 from the bottom. It leaves me only with the square root of x plus 3. So now I will try direct substitution, and I get an answer of 6. And in number 4, we have a compound fraction. So when I try direct substitution, I end up with 0 over 0. So I know I need to simplify this down. So I'm going to find a common denominator for the numerator so I can add these two fractions together. Adding the numerators, I get a 1 plus a negative 1 plus x. And then combining the two denominators, I get a negative 1 plus x over x. Simplifying the numerator, I end up with x on top, divided by x times the negative 1 plus x. Now I can cancel out the x from the numerator and x from the denominator, leaving me with just simply 1 over a negative 1 plus x. Again, I'm going to try direct substitution, and I cancel something out, and I end up with a negative 1. For number 5, it's the limit as x goes to negative infinity. So I'm going to use my n-behavior model to determine this problem. So that's 3x in the top and the square root of 4x squared on the bottom. Next thing I'm going to look at is if I simplify this, that's 3x over the square root of 4x, which means they occur at the same rate. So I'm going to look at the coefficients, which is 3 over 2. But I also need to check my signs and see if it's going to be a negative 3/2 or a positive 3/2. So plugging in our negative to the original n-behavior model, I get negative on top and a positive on bottom. So that means my answer is going to be negative 3/2. Okay, number 6 is another limit to infinity, so I'm going to try my n-behavior model. So that's going to be the square root of 3x squared over the square root of 3x squared. These grow at the same rate, and they happen to grow at a rate of 1. So my limit as x goes to infinity of this function is 1. Okay, for number 7, we have a limit as x goes to 3 from the positive direction. So first thing I want to do is see if I can factor the denominator. It does factor to x minus 3 times x plus 3, so I can cancel out the x minus 3 from the numerator and denominator. That leaves me with 1 divided by x plus 1. And then I can do direct substitution and end up with 1/4. Okay, looking at number 8 here, we're going to first try direct substitution. So that tells us we have something that we need to try to do something else with this equation. So my first approach is, let's see if it'll factor. And I notice it does factor, but I can't cancel anything out. And since I had division by 0 and then the top wasn't 0, I knew this wasn't the undeterminate form, so I probably wasn't going to be able to cancel anything out. But I notice I do have a vertical asymptote at x equals -1, which is where I'm trying to find my limit. So since there's a vertical asymptote as the limit as x goes to -1, I know that my answer to this equation is either going to be negative infinity or positive infinity, and I need to figure out which one. So I'm going to test points. I want to test a value just a little bit above and a little bit below -1 and see if I'm going toward a high negative number or a high positive number. So let's try -0.9, which is a little bit less, which is a little bit more than -1. So it's to the right of this. Plugging this into my equation, I don't really care exactly what the number is. I'm going to go ahead and write it down so that you can see, but the main thing I'm looking at is this going to be a negative value or is this going to be a positive value? And I end up with -300 and something, so I know it's a negative value. Just to double check and make sure the other side is also going to negative, I try something a little bit smaller than -1, so -1.1. Plug that in and let's see if I get a high negative number or if I get a high positive number. So I know if they're going to the same direction from the left as they're going from the right. And again, I end up with a high negative number, so we're looking at a -410. So my answer to this limit would be the limit as x goes to 1 of this fraction is negative infinity, because it's going to the negative from the left and from the right. Number 9 is a limit at infinity. I start by finding my end behavior model. In this case, that's 2x squared over 3x. That means the top grows faster than the bottom. So my answer is either going to be negative infinity or positive infinity. So I'm going to plug in a negative into the top and a negative into the bottom and simplify it down. And I realize that I'll end up with a positive in the numerator and a negative in the denominator. Positive divided by negative is negative, so my answer will be negative infinity for number 9. Number 10, I'll start by finding my end behavior model, which means I have a negative x in the numerator and a 2x squared in the denominator, so the bottom grows faster, so my answer is 0. On 11, we're going to find our end behavior model, which will be negative 3x squared over x squared. They grow at the same rate, so I'm looking at my leading coefficients, which would be -3. So my limit as x goes to infinity of this fraction is -3. Okay, number 12, we're given that f of x is equal to -x plus 3 divided by x squared plus 3x. And we're asked to figure out when this is continuous. And we know that the numerator is a polynomial and the denominator is a polynomial. So the only place this could be discontinuous is at our asymptotes. So I simplify it down, and I was able to cancel out the x plus 3, so that means I have a removable discontinuity at x equals -3. And then looking at my simplified fraction, it's now -1 over x. I have an x in the denominator, which means I have a vertical asymptote, which means I have infinite discontinuity at x equals 0. All right, and number 13, the first equation is polynomial, second equation is a polynomial, so that means it's continuous everywhere except maybe where the two halves meet. So I'm going to try by looking at my limit definition of continuity and figure out the limit from the left and limit from the right. The limit from the left is equal to 2. Now I'm going to substitute in the limit from the right, which this time I'll be using the bottom equation, which gives me an answer of -1. So since 2 is not equal to -1, this limit does not exist. Therefore, I have jump discontinuity at x equals 2. Let's start by factoring the denominator with the difference of squares. This allows me to cancel out the x plus 2, which means I have a removable discontinuity at x equals negative 2. Then my new fraction. Then looking at my new fraction, I have 1 divided by x minus 2. So that means I have vertical asymptote at 2, or I have infinite discontinuity at x equals 2. Number 15, I got a polynomial and a constant function, so it's continuous everywhere except at the point of the split. So I'm going to check the function for the limit from the left and limit from the right of 2. With the limit from the left of 2, I'm going to use the top equation, which will end up with the answer of negative 3. And then the limit from the right is also the top equation. Therefore, that will give us the same answer of negative 3. So the limit exists at 2, and the limit is negative 3, so I need to check and see if the function value is the same. So I check the function value at 2, and it's also negative 3. Therefore, this passed all the tests, and this is a continuous function. Okay, 16 looks intimidating with all the different equations, but if you take it step by step, it's not so bad. So let's look at part A. We were asked to find the limit as x goes to negative 4. So the first thing I need to do is figure out which equation I'm going to use for negative 4. Negative 4 is less than negative 3, so that means I'm dealing with the very top equation. So I'm going to find the limit as x goes to 4 of the top equation. All right, this is a very messy function, so I'm going to start by simplifying it down, especially after I try my direct substitution and end up with 0 over 0. So let's just figure out what x plus 1 plus x quantity squared is equal to. Then we're going to distribute the 2 to the second set of parentheses. Now I'm going to combine my like terms together. And on the top I end up with an x squared plus a 4x. And on the denominator, I still have x plus 4. And I notice I have a GCF of x in the numerator, so I'm going to bring that out. And now I can cancel out the x plus 4s. I have the limit as x goes to 4 of just x. So I can now try direct substitution, and when I plug in the negative 4, I end up with x is my limit is equal to negative 4. Part B, we're asked to find the limit as x goes to infinity of f of x. So infinity will be the last equation. Since this is the limit at infinity, I need to start by finding my end behavior model. So in the numerator, it's negative 4x cubed. Bottom, it's the square root of 16x to the 6. Simplifying that down, I get negative 4x cubed over a 4x cubed. So they occur at the same rate. So I'm looking at my leading coefficients, which will be negative 4 over 4, which is equal to negative 1. So my answer to B is negative 1. Part C is asked us to figure out what A and B is so that we have a continuous function. So first I'm going to start with figuring out a continuous function at 1. So I'm going to find the limit from the left of 1, which means I need to use the second equation. And then I want to find the limit from the right of 1, which means I need to use the next to the last equation, which is that bx squared plus a. Now, for the limit to exist, I know these two limits from the left must equal the limit from the right. I also know that it must equal the function value. So I'm going to decide to set this up as the limit as x approaches 1 from the left, which is 2x minus a, needs to equal my function value at 1, which is 3. Substituting in the 1, I end up with 2 minus a equals 3. Easily solving this equation for a, I get that a should be equal to -1. Now I'm going to look at the limit from the right to figure out my b value. I also know the limit from the right needs to be equal to my function value, which will be 3. So I'm going to substitute in the 1 in place of the x, and we end up with b plus a equals 3. Well, from earlier, I figured out that a is -1. So now in my b plus a equals 3, I can replace the a with -1 and solve for b. So to make this a continuous function, a needs to be equal to -1 and b is equal to 4. On question number 17, we want to see if does the intermediate value theorem apply to this situation. And well, we have to check the endpoints to see if it's continuous at the endpoints. As you can see from my work here, it is not continuous at the endpoint 4, because the limit as x approaches 4 from the right is equal to 5, and the function value at 4 is equal to 4. Since the limit from the right does not equal the function value, it's discontinuous at that endpoint 4, therefore I cannot use the intermediate value theorem on this problem. Okay, first figure out what g of 0 is. Well, looking at my graph, I see that g of 0 has a y value of 2. So since g of 0 equals 2 and exists, then we can say f of g of 0 is equal to f of 2. And then looking at our equation of graph of function f, we can easily see that f of 2 is continuous. So therefore, the function f of g of x is also a continuous function at the point x equals 0. Looking at part B, let's go the other direction. So we're going to start by finding what f of 0 is. Looking at our graph, so we're going to, since f of 0 is equal to 0, then g of f of x is equal to g of 0. And according to my graph, g of 0 is discontinuous. So I have jump discontinuity at that value. So therefore, g of f of x is also discontinuous. And remember, jump discontinuity means the limit from the left is not equal to the limit from the right. For our last problem, we're also going to look at intermediate value theorem. This time I was given the graph, and we cannot use the intermediate value theorem to prove that f of x equals 3.1415926 somewhere on this interval from 2 to 4, because if you look on the interval 2 to 4, it is discontinuous. And the main point is that the function value at f of 4 does not exist, but the limit is equal to infinity. So since the function value does not equal the endpoint value at 4, we know that we have a discontinuous function, and the intermediate value theorem does not work. But using my knowledge, I still know that there is a function value, f of x, which is equal to 3.1415926 on this interval, even though I can't use the intermediate value theorem to prove it. And how do we know this is true? Well, we know it's true because we have a vertical asymptote. And I can easily see that my function is going toward infinity on that vertical asymptote. So let's look at something a little bit less. So let's say at x equals 4, we have that vertical asymptote. And when we're looking for values less from 2 to 4, not including the 4, we do have a continuous function because it only fails continuity at that endpoint. And we take, say, f of 2, which is less than that 3.31415,926, and I know the limit as x goes to 4 of this function is equal to a positive infinity. Somewhere in there, I must hit the exact number 3.1415926. Part B. Let's look at each interval of continuity. So our first point of discontinuity occurs at -2. So notice that my -4, my endpoint is included, but my -2 endpoint is not included. For my next interval, it's continuous all the way until I hit 2. And my function value at my limits at my endpoints are not the same, so I do not include the endpoint values. Although here the function value at 2 is equal to my limit, so I do include that endpoint of 2, but I do not include the endpoint of 4. And then my next interval don't include 4 and don't include the 6, so it's from 4 to 6. And then I don't include the 6 and not the 8, so from 6 to 8. So that is all of my intervals of continuity for this graph.